Okay, in the previous video, we covered intramolecular forces, specifically ionic and covalent bonding. And in that video, we discussed how the periodic table tells us, based on where the elements are, whether or not they're going to ionize and form ionic bonds, or whether or not they're going to share and form covalent bonds. And we ended by talking about electronegativity and how we can use our rule for electronegativity, which is that oxygen is greater than nitrogen, which is greater than carbon, which is about the same as hydrogen. We can use that rule to help us determine whether or not a covalent bond is polar or nonpolar. And now we want to discuss why as we apply that to intermolecular forces, specifically hydrogen bonding. Hydrogen bonding is important because biology happens in water, and hydrogen bonding is intimately associated with water. And we'll see this in later units that specifically focus on water. But the hydrogen bond, let's come down here and let's define that. A hydrogen bond. We're going to give it a textbook definition, and then we're going to see if we can dissect that definition out to understand it. We're going to say this is a electrostatic interaction between electronegative elements that bridge a hydrogen. We could also say an electrostatic interaction between partial charges. And we'll see how this gets set up here in just a second. Let's go back to water. And we saw water up here. Let's come down and draw a new water molecule. We have oxygen, and we have two hydrogens. And we know that this is a polar covalent bond because oxygen is much more electronegative than hydrogen. That means that across this bond axis, we actually develop partial charges. A negative on the oxygen because that's where the electrons are hanging out, resulting in a positive down here. And same thing across this bond axis. So we have another partial negative here and another partial positive here. Now, one of the cool things about water is its cohesive properties. In other words, water sticks to water, and it sticks to water very well. Let's draw another water molecule, oxygen, hydrogen, hydrogen, and put in, once again, our charges. We have partial negative, partial negative, partial positive, partial positive. Now we can see why water sticks to itself so well. This right here is what we call a hydrogen bond. Now, if we go back to our definition, an electrostatic interaction between electronegative elements that bridge a hydrogen. We can see all of those elements here, right? We've got an electronegative element there, oxygen. We have another electronegative element there in another oxygen, and they bridge a hydrogen. The only way that they can bridge a hydrogen is if there's a polar covalent bond in there, or an electrostatic interaction between partial charges. So, electrostatic, what does it mean? Just like we talked about in the previous video, this is opposites attracting. Here we have a partial positive and a partial negative. They're not formal full charges like we see with the ionic bond, but they're similar in that they are both, the ionic bond and the hydrogen bond, examples of electrostatic interactions. The ionic bond just happens to be much, much stronger. So we've got an electrostatic interaction. It's a weak electrostatic interaction between partial charges, these electronegative elements that bridge a hydrogen. That defines our hydrogen bond. It doesn't always have to be oxygen. It could be, if we go back to our rule, right? It could be nitrogen, certainly. So let's take ammonia. Ammonia is NH3. So we have N, and then we have three H's. Nitrogen is much more electronegative than hydrogen. That puts on all of these hydrogens partial positives. This means that ammonia can participate in hydrogen bonding because it's got these partial positives on it. Now, the really important thing to recognize here, I can look at this molecule and I can say, it's soluble in water. Water will bind to this because water with its own partial charges can interact with it. So along comes oxygen, right, with its partial negatives. And there's the partial positives of my hydrogens. But right here, the positive and the negative, there's my hydrogen bond. Let me give you another example of how this works. Let's look at a molecule like glucose. Now, anybody who's made Kool-Aid knows that sugar dissolves in water. Well, now we can see why. Here's glucose, 1, 2, 3, 4, 5, 6 carbons, a double bonded oxygen there. OH, 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 OH. All of these, well, I guess before we start, let's make sure, because we know carbon has to make 4 bonds, we have to put in hydrogens. Usually we're lazy when we do this, and if we don't draw it, we just infer that it's a hydrogen. But now you can see that carbon is indeed making 4 bonds. But I really want to focus on these groups here, the O and the H. That is a polar covalent bond. Or the bond between the O and the C. That, again, is a polar covalent bond. And whenever I have a polar covalent bond, I have dipoles. And dipoles, by definition, are the separation of charge, these partial charges that exist on these elements. Along comes water. Water is covered, because it's a polar molecule, it's covered with these partial charges. It can interact with these parts of the molecule, and with water binding to the molecule, that means that that molecule will dissolve. And so we call it hydrophilic or soluble in water, simply because we know that it has these polar covalent bonds on it.